And he likes to make cyber-physical systems verifiable using real-time scheduling theory and formal methods. And he's going to talk about quasi-static scheduling for deterministic time concurrent models using multi-core hardware. Please.
All right. Hello, everybody. I'm very excited to be here today. My name is Xiaokai Lin from UC Berkeley, and the title of our work is Quasi-Static Scheduling of Deterministic Time Concurrent Models on Multi-Core Hardware. This work would not be possible without my amazing collaborators listed here, and some of us are on site this week. So let's dive in. Modern real-time applications demand both performance and predictability. One example here is the Ingenuity helicopter, which flew autonomously on Mars in 2021, which was very exciting. To achieve both goals, engineers have looked into static scheduling, which performs scheduling at compile time rather than at runtime. And quasi-static scheduling schedules mostly at compile time with some runtime decisions. And there are two benefits to quasi-static scheduling. Number one is there's almost no scheduling overhead at runtime, which makes it very efficient. And number two, schedules are open for rigorous analysis at compile time. And quasi-static scheduling has been studied for various models of computations in the past, including synchronous data flow, which we just heard about, Boolean control data flow, scenario-aware data flow, as well as logical execution time. However, these existing techniques, the quasi-static scheduling techniques for these models, are broadly similar. So the research question that we ask in this work is, can we somehow unify them? And there are two benefits to such unification. Number one is that this will provide a common framework for comparison. So we know how these existing techniques differ from each other, how similar they are, as well as how they're different. And second, this unification makes it easy to reuse techniques for future applicable models of computations. So in a nutshell, our work is a unified approach. First, we present a unified quasi-static scheduling approach based on state space finite automata, SSFA. And this is an intermediate formalism bridging high-level models of computation and low-level implementation. Second, we present a class of models named Deterministic Time Concurrent Models, DTCMs, where the unified approach applies. And third, we demonstrate our quasi-static scheduling approach on reactors and emerging models of computation. And lastly, we evaluate the performance as well as analyzability of our approach using a benchmark and a case study. So next, let's dive into this formalism of state space finite automata, SSFA. In a nutshell, SSFA is a state machine of DAG tasks. As you can see from this formalism, you can find the familiar components that you'll find for a extended finite state machine. So you can see the modes, you can see the transitions, variables, guards, as well as the initial mode. So what sets it apart is the D function that assigns a DAG to each node. As you can see within each box that we have, here's the DAG inside. So let's zoom into the DAG and see it a little bit better. So here we use a DAG representation that encode real-time constraints. So below the dash line, there are tasks with dependencies, where tasks are nodes, are the circles, and dependencies are the arrows. And above the dash line, we have virtual nodes encoding real-time constraints. And you can find that there are two layers of the virtual nodes. The lower circles encode physical time points, whereas the upper circle encode time durations between two consecutive time points. And using this representation, we can encode the notion of release time and deadline. So now we know what a state space finite automata is and what each DAG inside looks like. Next, let's focus on how to schedule a state space finite automata on multi-core hardware. And in this case, scheduling an SSFA means partitioning each DAG in the SSFA by doing two things. Number one, we want to assign each task to a core. And number two, we want to sequence the tasks assigned to this same core and essentially create a linear sequentialization among these tasks. So assuming that we have two cores and we have this DAG on the right-hand side, let's do this procedure and see it in action. So we can see that here, after partitioning, here we have two partitions, one blue and one red, where the blue partition is mapped to core 0 and red partition is mapped to core 1. And if all timing requirements satisfied, which we can check by analyzing this DAG, we consider this new DAG to be trivially schedulable. So what are the properties of trivially schedulable DAGs? We'll dive into this next. So property 1 is anomaly-free timing. And in this case, anomaly-free means monotonicity. Intuitively, this means that when an individual task increases or decreases its execution time, the overall make span does not change in the other direction, meaning that there's no surprises. And in the paper, we have a theorem 4.1, which is about this monotonicity property. Let's see this property in action. So on the right, we have a trivially schedulable DAG. And assuming that we have two cores, this make span of executing this DAG is 6.1. So now let's try to shrink one task's execution time. So let's pick V2 and shrink it down from 1.1 to 0.9. We can see that the corresponding make span also shrinks in the same direction from 6.1 down to 6.0. What happened to the reverse scenario? So let's now pick another node, V1, and bump its execution time from 1 to 1.2. And now we can see that the make span also bumps in the same direction from 6.1 up to 6.2 in the same direction. So this example demonstrates monotonicity. And this property also holds without requiring knowledge about WCETs, because we can see that the pattern also exists without knowing the precise numbers within the circles. So that's property 1, anomaly-free timing. Let's get to the next property, which is analyzable make span. So the DAG representation yields a very straightforward dynamic programming algorithm to check make span up to some node. So here, let's assume that we have a node n in this box with a deadline of 12. And by executing this DP algorithm, essentially by tracing back linearly up the dependency chain, we can generate the equation down below. And you can see that there's a max turn inside, and that comes from the fact that at one of the blue nodes on the right, the third blue node, we actually fork off two different paths. So we have to take the maximum along each path. So having done this calculation, we can find that the make span up to node n is 11, which is less than 12, the deadline. So we can make sure that this deadline will not be violated. And next, let's talk about deterministic time concurrent models. The definition, and we'll also give some examples, including synchronous data flow and the subverging model co-reactors. So what is it? DTCMs are a class of models of computation such that each model defines a finite set of execution phases, P. And each phase is deterministic. And then lastly, the model defines transitions between phases, and the transitions could be non-deterministic. And the key idea here is that a DTCM's behavior can be modeled by an SSFA, which is the formalism that we introduced earlier. So let's use the example of the synchronous data flow. On the left-hand side, we have the synchronous data flow graph. And on the right-hand side, we have a acyclic precedence expansion graph generated from the left-hand side. And you can think of the right-hand side as the DAG that represents the behavior of the periodic behavior of this SDF graph. So let's run the checklist. Does it have a finite execution phases? Yes. In this case, on the right-hand side, there's only one DAG. So effectively, there's only one phase in the steady state of the SDF. So let's check that box. And the second thing is we want to check if each phase is deterministic. In this case, it's also yes, because the DAG here represents one unique partial order of the active firings. So that's determinism. And number three is there phase transitions defined by the model? In this case, this is trivially true because every time we finish executing the DAG, we just go back and do it again. So there's a trivial self loop defined between two consecutive phases. So it is a DTCM, and we can turn this into an SSFA by wrap this DAG into a mode by drawing a box around it, and then give it a self transition with a guard of true. So that becomes the resulting SSFA for this program. Now let's take a look at a slightly more non-trivial example using a different model called a reactor model. So on the right-hand side, you'll find this system represented as in the reactor diagram. And in this case, I'll show the SSFA directly. In the paper, we discussed in detail how this SSFA is generated using a state space exploration algorithm. But for the sake of time, I'll skip over detail in the talk and invite you to check out the paper. So here's the SSFA that corresponds to the reactor diagram. And let's run the checklist again. So does it have finite execution phases? Yes. In this case, we can see that there are 3 different modes, which is finite. And each phase is deterministic because each phase contains one unique DAG, which represents the unique partial order of active firings. And then lastly, there are phase transitions defined between phases. You can see that here there are 2 default true transition and 1 guarded transition that checks whether the time is greater than some sort of timeout value. So reactor is also a DTCM. And now the next pressing question that we want to explore is, given this SSFA, how do we actually implement the quasi-static schedule in low-level implementation in code? So this is what we'll explore next. And I'll talk about generating these executable schedules based on an intermediate representation. So here is an example of a partition DAG on the right-hand side. So how do we execute the blue partition? Well, the strategy can be pretty simple for the blue part, which is the core 0 executing this blue region can do these tasks in the order of dependencies. And as soon as it finishes one task, it will update a counter in this that belongs to this blue region. And then they can do it all the way until the DAG is finished, and then evaluate the guarded transition at the end. For the red, the strategy can start out pretty simple as well. So it can do task G11 and then update its red counter. However, it gets a little bit complicated for the second one because we have to wait until the blue P11 to be done, then go ahead and execute P21. So at line 3, core 1 has to wait until blue counter reaches 3, and then it will proceed until the DAG is done. So we developed an IR that encodes the semantics of these instructions in the form like this, and we implement this IR generation logic by extending the reactor toolchain. So here is the compiler architecture for reactor systems. based on a language called lingua franca. And the colored boxes here are our work. We basically extend an existing compiler to be able to generate this executable schedule on the top right. So how does the performance look like, which we'll talk on next? Using the reactor toolchain, we evaluate the performance of our quasi-static scheduling compared to the performance of the default dynamic scheduling. The experiments are run on a Raspberry Pi 4 with a QNX real-time operating system. In this work, we implement two quasi-static schedulers, which correspond to the maroon and purple clusters, and the dynamic scheduler corresponds to the orange cluster. To quantify performance, we measure a property called lag, which is the difference between the physical timestamp at which a task is invoked and the logical timestamp at which it should be invoked. And in this case, the smaller the lag, the better the performance. And we can observe that the quasi-static schedulers have smaller lags and smaller spread in the distribution. And across our benchmarks, the performance improvement of the quasi-static scheduler over the dynamic scheduler is on average around 9 times, and the median is around 3 times to 4 times. Let's move on to the second evaluation, which is compile time deadline validation. We evaluate the soundness of our compile time deadline validation using a case study. So here we have a non-trivial satellite attitude control system with 2 deadlines, one attached to the gyroscopes and another one attached to a motor. Given individual tasks, WCTs, measured by the WCT analyzer Platin, the compiler asserts that all deadlines are met. However, is this assertion correct? We run the system on the FlexPred processor and record the firing time points of these tasks. And on these graphs, we see that the deadlines, the actual measured firing times, do not exceed the deadlines. And so in practice, no deadline gets triggered. Hence, this shows that our deadline validation at compile time is correct, at least in this specific example. So here are the takeaways. Number 1, we present a quasi-static scheduling approach based on a new intermediate formalism called state-space finite automata, which is free from timing anomalies and enables compile time deadline validation. Number 2, the SSFA-based approach unifies quasi-static scheduling for deterministic time concurrent models, DTCMs, which includes SDF, UDF, LET, SADF, as well as reactors. Number 3, we compile scheduled SSFAs to an intermediate representation. Each core interprets its own executable schedule written in this IR. And number 4, experiments show that quasi-statically scheduled reactor programs deliver on average around 9 times performance improvement compared to the default dynamic scheduler and supports compile time deadline validation. So if you want to learn more about this work, I invite you to scan this QR code, and I want to thank you for your attention.
Thank you very much. Any questions from the audience? Yes.
Thank you very much for your talk. I was wondering if the model that you presented, if it assumes that the individual phases of execution are executed sequentially, so one phase ends before the next one is started. Because I guess some of the models that you are unifying, like SADF, would actually allow for these phases to be pipelined to sort of overlap in time. But is that something that you consider that fits in the framework?
Okay, so when we consider SADF, we indeed make that assumption, which is we assume that one SDF graph is finished and then move on to the next. So in the case of being able to pipeline SADF, we did not consider that case. Yeah. But I'd love to chat with you more about that offline.
Right?
Thank you for your talk. I can see from the reactor diagram that you have many components which are somewhat modular. And then when you perform the compilation to SSFA, you flatten this into a single finite automata. So if you were to introduce an additional component, I assume you'd have to recalculate the entire SFAA. And so I think usually with these types of approaches, you often see stack space explosion for more complicated systems. Is this something you worry about?
This is something that that I do worry about, and in this work, all the analysis is done globally. But one of the future work direction is to see how to enable compositional analysis, like you mentioned, where state space do not have to be calculated all over again. But yes, I think that's a great point. Thank you.
In that respect, could you do some approximations? So say, for example, you have a set of states and then you say these have to be executed, so these have to be blue, and you mark them.
Are you referring to the DAG representation? Or?
So I'm referring to the SSFA. If you take that and then you say, for example, here you would say these three nodes that were blue, you have to execute them sequentially and you schedule them on the same core. And then you treat them as one single node.
I see. So are you referring to across two separate runs? You reuse the previous assignment?
Exactly.
Oh yeah, I think this is definitely possible, yes. If we are willing to give up some global optimality, we can reuse the prior results and make some tweak the previous schedule a little bit and adapt it into a newer schedule.
And maybe then you avoid the state space explosion for
Right.
the future runs.
Yes, I think that could be one direction, yes. Thank you.
I wonder if you can say how you do the core petitioning and whether bad petitioning can prevent you from scheduling a system that would be schedulable otherwise.
Yes, that's a very good question. So, in this work, we primarily consider partition-based DAG scheduling, and DAG scheduling is actually a fairly sizable community. There are many researchers working on how to partition DAGs to meet the real-time constraints. So the only requirement that we impose in this work is that the DAG scheduler needs to use the representation that contains these virtual nodes. So let me see if I can find it. Yeah, right here. So as long as the DAG scheduler can handle these sort of DAG inputs and be able to partition the DAG, this DAG scheduler can be plugged into our current infrastructure. Now, if the DAG scheduler makes a bad decision, for example, assigning everything to one core and leave the other complete idle, in this case, yes, the deadlines will not be able to be met, and we would leave this optimization to the DAG, to the implementers of the DAG schedule. And in this work in particular, we use a scheduler called the edge generation scheduler, which satisfy the requirement that we made.
All right, thank you very much.
Thank you.